Good morning, students. Today we are going to learn about elementary transformations of a matrix. There are 6 operations or transformation on a matrix. 3 are due to rows and 3 are due to columns, which are known as elementary operations or transformation. Number 1 operation is Ri double arrow Rj denotes the interchange of ith row and the jth row. This notation represents the interchange of ith row and the j column. Sida piriba ith row haibasiga j row haibasiga interchange tawbasa sigi representation sina piraniba. Then the corresponding column operation is denoted by the symbol Ci double arrow Cj denotes the interchange of ith column and the j column haibadi R iragana rows the interchange tawba ko C iragana columns the interchange tawba. Then example apply to say applying R1 double arrow R2 to matrix A. Elements are 1 2 3 4 0 2 0 2 3. Step piriba R1 ga R2 ga interchange tawba haiba operation se matrix A de apply tawrase. Sigi operation se matrix A de apply taw tardi first row becomes second row and the second row becomes first row. Step piriba first row se second row and this second row becomes first row. Sina kay de apply tawi rows ta in a column de apply taw tardi first column should be interchanged with second column. First column ga second column ga interchange tawrani. Next second operator is Ri tends to k times of Ri, where this k is a scalar, denotes the multiplication of each element of the ith row by a scalar k, where k not equal to 0. Stepiriba notation sina kay denotes the v hai taradi. This denotes all the elements of the ith row multiplied by a scalar k, where k not equal to 0. Nangi k se 0 gamana beade. And the corresponding column operation is denoted by Ci tends to k times of Ca. Sigi representation china kai hari no haradi all the elements of the ith column should be multiplied by this constant k. Add kaida tawgani ith suba column sida ko example. Applying R1 tends to 2 times of R1 to matrix A. Matrix A is a square matrix of order 3. Then we apply this operator on this matrix A. Then we get R1 tends to 2 times of R1 means all the elements of the first row should be multiplied by 2. Nangi first row gi element nam se 2 na multiply tawrni adu disigi sida 2 na multiply tawrsiko. 1 into 2 is equal to plus 2. 2 into 2 is equal to 4 and 3 into 2 is equal to 6. Main tawraga koina sige operator se matrix A de apply tawradi we get this matrix. Similarly for the column matrix ta hairamagadi kamai chetkani C1 tends to 2 times of C1. C1 tends to 2 times of C1 means all the elements of the first column should be multiplied by 2. 2 na multiply tawgani. Then this 1, 4 and 0 should be multiplied by 2. 1 into 2 it should be equal to 2 and 2 into 4 it should be equal to 8 and 2 into 0 which is equal to 0. Then remaining columns will be same. Nangi remaining columns sing the same orani ba. This main tawraga koina operators ani tami ko first operator second operator. First operator dasu row ga column ga dalera second dasu row ga column ga dalera aduna elementary transformation se sibau the mari tami. Next operator number 3. Ri tends to Ri plus k times of Rj. Denotes the multiplication of each element of z row by k added to the corresponding elements of the ith row. Sigi representation sina kai hari no haradi. First, all the elements of the z row multiplied by constant k and added to the corresponding elements of ith row. Nangi ith row subasida hapsen gani kamai hapsen gani. Then the corresponding column operation is denoted by chapma nana sigu operator se kaide apply torsiani columns de apply torsiani ko. The example yang say applying R1 tends to R1 plus 2 times of R2. Sina main torse kaina. What does this notation represent? Then first we have to multiply all the elements of the second row by the scalar k. Scalar k here k is equal to 2 and adding to the corresponding elements of first row, and we should apply this operator on first row they apply tawgani ba. Jodi khoi step matrix A empirical matrix A sida kanana hana multiply tawgani. All the elements of this second row should be multiplied by 2 and 4 into 2 which is equal to 8 and 8 plus 1 it should be equal to 9. then 0 into 2, 0 into 2 is equal to 0, and 0 plus 2 is equal to 2. Then 2 into 2, 2 into 2 is equal to 4, and 4 plus 3 is equal to 7. Then write the remaining elements. Remaining elements are 4, 0, 2, and 0, 2, 3. Sumain tawraga koina apply tawgadabse karamba row khatangda apply tawgani. We should apply this operator only on first row. First row khatangda apply tawniba. Then siga chap manaba case kaidasu hotpa yagani, column operation dasu hotpa yagani ko aduna operators se kya lere, 6 operators lere. There are 6 elementary transformation that can be applied on matrices. 3 are due to rows and 3 are due to columns. Ahum amana rows te apply to yagani, ahum amana columns te apply to yarni ko. Next, let's define invertible matrices. If A is a square matrix of order M, and if there exists another matrix B of the same order M such that A into B equals to B into A is equal to I, then B is called the inverse of the matrix A and is denoted by A to the power minus 1. Koina number da khangise ko 2 into 1 by 2 is equal to 1, and also 1 by 2 into 2 is equal to 1. 1 by 2 da 2 na multiply to basa adum 1 thani ba. Then kaina kai khanges dagya 1 by 2 is the inverse of 2, and 2 is the inverse of 1 by 2. 2 gi inverse 1 by 2 neba. 1 by 2 gi inverse 2 thani ba. Maramdi kaigino product of this number is equal to 1. Since 1 is the identity element in multiplication. Multiplication ki identity element se 1 ni ko. Similarly for the matrix. For any matrix A, if there exists another matrix B such that A into B and B into A is equal to identity matrix. Identity matrix, then B is called the inverse of matrix A, which is denoted by A inverse, and therefore this matrix B should be multiplied by, it should be represented by A to the power minus 1. A into A to the power minus 1, A inverse dot A, it will be equal to I. Sumain taraga koina inverse ki definition se PVR ko. Next, theorem number 3. Uniqueness of inverse. Theorem number 3, 2019 da hangi ko, carrying 2 marks. Inverse of a square matrix, if it exists, is unique. Inverse of a square matrix, if it exists, is unique, which means that inverse of every square matrix is unique. Unique means ama khatang lay heba ko. Inverse of square matrix se ama dagi henba yade heba. Prove tawrisi ko. Let us prove this theorem. Let A be a square matrix of order M. A is a square matrix ni ko order M. If possible, let capital B and C be the inverse of matrix A. B ga C ga sa kanagi inverse ne na lower koina B and C are the inverse of the matrix A. Then we shall prove that B is equal to C. B ga C ga sa ina A gi inverse ne na lower matamda kai prove tawrani. Matrix B is equal to C. Si prove tawdoini. Since B is the inverse of matrix A, by definition of inverse of matrix B, we have A into B equals to B into A is equal to identity. Write equation number 1. Since C is the inverse of matrix A, then AC equals to CA is equal to identity. Write equation number 2. Thus, this matrix B can be expressed as B into I. B into I means identity matrix. Then B is equal to, this I is replaced by the expression AC from equation number 2. 2 da yariba sige I gi mahut sa kay na singrani, AC sina singrani using 2. Then by associativity of multiplication of matrices, B into A into C, it is also equal to product of A, B and C. Ani se gyana product hole ko C tare. Then BA. This BA is represented by matrix I. Using equation number 1, then I into C, it will be equal to C, since I is an identity matrix in identity matrix, and therefore this matrix B is equal to this matrix C. So the inverse of every square matrix is unique. Next theorem, theorem number 4. Theorem number 4, so 2019 da hangi ko. Statement: if capital A and the B are invertible matrices of the same order, then the inverse of product of AB, it will be equal to B inverse into A inverse. Product of AB, it will be equal to B inverse, and A inverse means the inverse of product of two matrices is equal to the product of inverse of the matrices taken in reverse order. Reverse order de lakaniba. Maramdi A B harambaza. Next B inverse into A inverse and lani. Then let's prove this theorem. Proof from the definition of inverse of A matrix. We have AB into AB inverse. It will be equal to I. By definition of inverse of the matrix, since the product of AB is also matrix and AB product inverse is also a matrix. Then we have to eliminate this A and the B from left hand side. For this, we should multiply both sides of the equation by multiply A to the power minus 1. Pre-multiplying both sides of left hand side and right hand side by A inverse. A inverse AB inverse will be equal to A inverse dot I. By associativity law, it can be expressed as A inverse A multiplied by B, AB inverse, which is equal to A inverse into I is equal to A inverse. By definition of inverse of square matrix A, which is equal to I, then write B, write AB inverse equals to A inverse. I into B, it will be equal to B, AB inverse is equal to A inverse. Then, to eliminate this matrix B, we have to multiply both sides of the equation by B inverse. B inverse B, AB inverse is equal to B inverse dot A inverse. B inverse B, by definition of inverse of the matrix B, it should be equal to I, AB inverse, which is equal to B inverse into A inverse. Since I is an identity matrix and I into AB inverse, it will be equal to AB inverse equals to B inverse into A inverse. So, left hand side is equal to right hand side, hence proof. The proof theorem. Next, algorithm for finding the inverse of non-singular square matrix by elementary row transformation. Koina any matrix ama nongonda pire. Matrix egi inverse kamain puthokani haitaradi row kya method kya da puthokpe yare ani da puthokpe yare ko. We can find the inverse of a non-singular square matrix by two methods. Number 1, row transformation, and number 2, column transformation. And first operation is row transformation. The important steps are: number 1, write the square matrix A. Square matrix A ama iro ko. The square matrix A means let the given matrix is represented by the square matrix A. Step number 2, write A is equal to IA. Step number 3, apply a sequence of elementary row transformation on this matrix equation. A is equal to IA until we get I will be equal to BA. This matrix A, it should be converted into matrix I. Then this matrix I is converted into another matrix B, and matrix A is same as A. Then we get another matrix equation. I is equal to BA. Then write B is equal to A inverse by the definition of inverse of any matrix A. For any matrix A, there exists another matrix B, and A multiplied by B is equal to identity. So the inverse of A should be equal to this matrix B. For step number 3, apply a sequence of elementary row transformation. This elementary row transformation will be these operators. Si operators hoidini ko. Kuna first kaidawni. There is a matrix of square matrix of order 3 whose elements are A11, A12, A13, A21, A22, A23, A31, A32, A33, and these elements are to be represented by any real number. Any real number amna represent tawdoneba. Aduna in the first sige elements kanaga compare tawgani. Compare all these elements with the identity element of order 3. Compare tawsiko. A haiba elements in the sin orakadoneba. Sina matrix A have a C oidoneba. Dudi matrix A se I tanava kamain semni haitar dimagi steps se number 1 da sige 1 se C1 tahandoineba. The elements in first row and the first column should be equal to 1. So the element A11 should be equal to 1. This is the first step. Row se first row, second row, and the third row. Simong chattunika. By using this element 1 in the first row, then make the corresponding element A21 and A31. A21 in the second row the labani, A31 in the third row the labani. Moibanik se kaigamana ba same gani, it should be equal to 0. This is the second step. In the first step ka in the second step. Next, diagonal element A22 should be equal to 0. This diagonal element should be equal to 1. 1 tahandoini ko. See 1 tahala, this in step number kya tarani 3. By using this element 1 in the position A22, Then kailane corresponding element A12 and the A32 should be equal to 0. This is step number 4. Then make the diagonal element A33. Kya ga mananaba semgani? It should be equal to 1. 1 tareko. This is step number 5. Step number 5 ne. Then make the corresponding element A13 and A22. Sila adi sumay chat kedoine. Duna sigi element sa kya ga manhalani 0. Sine step number 6. Sinataba to be apply to Rusuyani ko. Next, algorithm for finding the inverse of non-singular square matrix by elementary column transformation. Elementary column transformation used the inverse puthokpa. Steps are: step number 1, write the square matrix A. Step number 2, write A is equal to I by A. For row transformation, which is equal to A is equal to I into A. And this is the change legani. Step number 3, apply a sequence of elementary column transformation on the matrix equation A is equal to A multiplied by I till we get the matrix equation I is equal to AB. For this matrix equation, this I becomes identity, and this A, and the I becomes B. And so B will be equal to A inverse. Sigi matrix B sa kanagi inverse tarani, A inverse tarani ko. Number 3, sequence of elementary row transformation will be like this. Compare these elements with the identity matrix. Identity will compare to Rosika. First, the A11 element lies in first row and the first column, it should be equal to 1. When the first the A11 say 1 dana same gani, but this is the first step for column transformation. First column, second column, and the third column. By using this element 1 in the first column, we have to make corresponding element A12 and the A13, which is equal to 0. This is step number 2. Then step number 3, make the diagonal element A22 unity. By using this element, the corresponding element A23 and the A21, it should be equal to 0. Si ani simog 0 tahalani ko. Sin is step number 4. Then last, the diagonal element A33, it should be equal to 1. 1 ga tanaba semo. Step number 5, and the last step is corresponding elements A31, A32. These two elements should be equal to 0. This is the last step. Sinataba top step apply to Vayani ko. Remark: after applying one or more elementary row or column transformations on the matrix equation, this equation or this equation, if we obtain all zeros in one row or more rows or columns of the matrix A on the left hand side, then A inverse does not exist. Koina elementary transformation je taruk ne. Taruk to gi manung da ama apply to matamda nangi left hand side the piriba matrix A gi one rows or all the columns or one column or all columns loina zero phangagadi adugi matrix to akai leitaba kaurane A inverse does not exist. A inverse puthokpa ngamaroi. Exercise 3.4. Here we have to find the inverse of each matrices if it exists by using elementary transformations. Number 1. Row column we can find the inverse of any square matrix by using row transformation or column transformation. For this, we have to find the elementary transformation only. Let A. Question number 1. Let A represent a given matrix whose elements are 1, -1, 2, and 3. 2 ga 3 ga period. For row transformation, this matrix A is equal to I into A. See equations E gadam. Step number 1, step number 2, then step number 3. Apply horosiko. Sigi nang na tahalakadav se 1 0 0 1. Si tahanab se magtuine bako. Sigi matrix A se. Do the 1 -1 2 and 3 1 1 chapmanareko. Here A1 1 element lies in first row and the first column is equal to 1, so we skip first step. First step skip the record. Si chapman ire. Then by using this element 1, make the corresponding element 2 in the second row is equal to 0. Sigma na the same move. Applying R2 tends to R2 plus -2 R1. Chikamay la ino harade. 2 se kaide lies the way. Since 2 lies in second row, first right second row tends to write this row R2 irasiko plus we use 1. Since 1 lies in first row, write R1. Then we need another scalar. Scalar mchangeko plus 2 oitardi, scalar should be -2. If it is -2, then scalar should be +2. Opposite sign lowgadaba. R2 tends to R2 plus -2 R1 we get. Sina mentor se kaino. First, all the elements of the first row multiply by -2. First row se -2 na multiply the row and are added to the corresponding element of second row, and this operator is to be performed on second row. Second row they apply the gunibako. So there is no sense in first row. First row the sense clear. Then 1 minus 1 ireko 0 1. Sigo operators left to apply the guni, right to samana apply the ni. The first 1 multiplied by -2. -2 plus 2, which is equal to 0. -1 into -2, minus plus 2 plus 3, which is equal to 5. Then apply this operator on right hand side also. 1 0 and 0 1. So they apply to Horsika. 1 0 and itoe. Then multiply this first row by -2. 1 into -2, which is equal to -2. -2 plus 0 is equal to -2. Then 0 into -2 is 0. 0 plus 1 is equal to 1. Corresponding element the hapkan himay mapachana sana basis the hapkan him multiply by matrix A. Silereka. Si 1 legre, si 1 legre, si 0 lereka, si 1 tana basem se. Si 1 tahan gi di ko na kamay tao ni. Si 1 se fix lereka. Ko na fast row fix the grass tends to adre. Applying R2 tends to R2 by 5. Second row is the 5 na divider. The 5 divided by 5. It should be equal to 1. 1 tani. The second row tends to R2 by 5. We get R2 by 5 means all the elements of second row should be divided by 5. 5 na divider to 1 minus 1 ire. 0 divided by 5 is equal to 0. 5 divided by 5 is equal to 1. 1 0 ire ko. -2 by 5 is equal to -2 by 5. 1 by 5 which is equal to 1 by 5 multiplied by matrix A. G1 tare, china -1 later ko. By using this element 1, make the corresponding element -1 is equal to 0. 1 plus -1 is equal to 0. So applying R1 tends to R1 plus R2. This -1 lies in first row. So we have to write R1 tends to write R1 plus R2. 1 plus -2 is equal to 0. So the scalar is equal to 1. 1 equals the scalar se. And is a plus the over se first row the hapas equal 0 plus 1 is equal to 1. 1 plus -1 is equal to 0. 1 plus -2 by 5. 1 plus -2 by 5. LCM lower the 5 tare 5 minus 2. Kya gamanare 3 by 5. And 1 by 5 plus 0 which is equal to 1 by 5. Then write all the elements of second row. Second row ito. This is the 1 0 0 1. Matrix A becomes identity matrix. So A multiplied by this matrix is equal to identity matrix. By the definition of identity matrix, A inverse should be equal to this matrix. The variable matrix है kanagi inverse tarani A inverse के matrix orani. Next question, question number 2. This is the last question. Question number 2, the matrix empirical. There is a matrix A represents 2 1 and 1 1. By using elementary row transformation, find the inverse of this matrix. Step number 1, write A is equal to I into A. Write elements A, write identity matrix of other 3A. Step number 3, apply a sequence of elementary row transformation. Number 1, 2 1 1 1 1 0 0 1. So na 1 like rest and a 2 layer gone. To the 1 0 and 0 1 si tana ba same doing. Kana intersense to where first row ga second row intersense to risika. Applying R1 tends to R2 we get. This intersense to we should apply this operator on left hand side and right hand side also. First row ga second row on thong na reka. First row becomes second row becomes first row and the first row becomes second. For this first row becomes first row se second row and the second row becomes first row. Chan ito ko A layer 1 bhange ko 1 bhange. By using this element 1, make the corresponding element 2 equal to 0. Applying here the elementary transformation is, since these 2 lies in second row, R2 tends to write this R2 iroka. here we have to use fast draw, right? Fast draw, then find the scalar. Find the scalar to make this 2 is equal to 0. 1 the multiply tꯧꯒꯗꯕ scalar ꯗꯣ ꯈꯜꯂꯣꯕ ꯀꯅꯥ 0 ꯇꯥꯍꯟꯅꯕ 2 ꯁꯦ 0 ꯇꯥꯍꯟꯅꯕ ꯑꯗꯨꯗꯤ 1 into minus 2 which is equal to minus 2 and minus 2 plus 2 ꯍꯥꯏꯔꯗꯤ ꯀꯩꯒꯤ ꯇꯥꯔꯅꯤ 0 ꯑꯗꯨꯅ scalar ꯁꯦ plus 2 ꯂꯩꯔꯝꯃꯗꯤ minus 2 ꯂꯧꯔꯅꯤꯕ r2 tends to r2 minus 2 into r1 ꯁꯤ operator ꯁꯤ 이래ꯀꯣ ꯃꯥꯅ mean ꯇꯧꯔꯤꯁꯦ ꯀꯩꯅꯣ first all the elements of the r1 should be multiplied by minus 2 and adding to the corresponding elements of second row the half of 1 into minus 2 minus 2 minus 2 plus 2 is equal to 0. 1 into minus 2 minus 2 minus 2 plus 1 which is equal to minus 1. Sida fast row yaudamne fast row sense laite ka 1 1 0 1 itoe. The 0 1 ire multiply elements of fast row by minus 2. 0 into minus 2 0. 0 plus 1 is 0. 1 into minus 2 which is equal to minus 2. Minus 2 the 0 hapsiladi minus 2 dum tare ka. Then write matrix A. 1 phange 0 phange minus 1 tare. Minus 1. Sida nangi minus 1 is done hapsilamo 0 tanabako. Then applying r1 tends to r1 plus r2. Nangi first row se find the sum of first row and second row. First row ga second row ga plus tau tho. Sida hapsille 0 chale minus 1 plus 1 is equal to 0. 1 plus 0 is 1 minus 2 plus 1 which is equal to minus 1 multiplied by matrix A. Then make this element minus 1 is equal to plus 1. For this we should multiply all the elements of second row by minus 1. Minus 1 multiply taurani. To the minus minus plus tareko 1 0 and 0 1. 1 1 into minus 1 is equal to minus 1. Minus 2 into minus 1 minus minus plus it should be multiplied by matrix A. For any square matrix A, there exists this matrix and A into this matrix is equal to identity matrix and therefore A inverse will be this matrix whose elements are 1, minus 1, minus 1 and 2. Sumain tawraga koina inverse puthokpa yaiba by using row transformation. Sige this the lawyers.